Hey everyone, and welcome to this explainer. Today, we're diving straight into an invisible mathematical force that is constantly shaping your wallet, your savings, and, well, the entire global economy. It's an absolutely foundational concept in finance, and I promise you, by the time we wrap up today, you're going to look at every single purchase or investment you make through an entirely new, incredibly powerful lens.
Let's kick things off with a quick mental exercise. Would you rather have 100 pounds right now, today, or 105 pounds in exactly 1 year? Intuitively, you might actually have to pause and think about it for a second. Because if you take that 100 pounds today and invest it at, say, a 5% interest rate, assuming zero inflation, just to keep it simple, it's going to grow into 105 pounds in 1 year anyway. So mathematically, to someone expecting a 5% return, both of those options actually have the exact same value. It's wild, right? And that little mental exercise is really the beating heart of our entire topic today. So here's our roadmap for today. 1. Money today versus tomorrow. 2. The math of time. 3. A centuries-old concept. 4. Everyday time value. And 5. The infinite math. All right, jumping right into section 1. Money today versus tomorrow. The invisible force shaping your wallet. The absolute core idea we're working with here is called the time value of money. But why does money's value actually change just because the clock ticks? Well, it essentially boils down to earning capacity and, frankly, human impatience. A chunk of cash right now provides a way bigger benefit than that exact same amount later, because money in your hand today can be put to work immediately. You can earn a positive return on it and produce more money for tomorrow. Economists call this time preference. Basically, it's impatience. We overwhelmingly prefer having things right now rather than waiting.
To kind of map this out in our heads, think of valuation like two opposite poles. On one side, you've got present value, which finance folks often call times zero. And on the far side, you have future value, which is just the value of an asset at some specific date down the road. The whole concept of the time value of money is simply comparing cash flows that happen at different dates. We do this by mathematically converting them so they can sit side by side on a single comparable date.
So what's literally driving this change in value over time? Think of it like a massive financial tug-of-war. Pulling on one side is opportunity cost. If you spend your money right now, you completely lose the opportunity to save or invest it. And that is exactly why interest exists in the first place. It's there to compensate you for losing the use of your cash. But pulling hard on the other side of the rope is inflation. For it to actually be worth parting with your cash today, your future return doesn't just have to offset your impatience, it literally has to outpace the rate at which inflation is eating away at your purchasing power.
Moving right along to section 2, the math of time, mapping the variables.
Now, I know formulas can sometimes be a bit dry, but please don't let the algebra intimidate you here. We really only need 4 basic variables to unlock all of these calculations. We've got PV, which stands for present value. We have FV for future value. Then there's I, which is our interest rate, that's the compounding rate per period, and finally N, which stands for the number of periods, like months or years. Whether you're a Wall Street banker valuing massive corporate debt, or you're just looking at your own savings account, these 4 variables are basically your master keys.
Okay, so if we want to figure out what our money is going to be worth in the future, it's just a simple 3-step journey. Step 1, you start with your present value. Step 2, you multiply it by what's called the accumulation factor. That's simply 1 plus our interest rate, raised to the power of our periods, so 1 plus I to the power of n. Do that, and step 3, boom, you arrive at your future value. This is the bedrock formula for the time value of money. Every single other formula we talk about is derived directly from this one simple relationship.
But what if we want to throw the math into reverse? Say you know for a fact you're getting a lump sum in 10 years, but you want to know what it's worth today. To find that present value, we take the future value and multiply it by a discount factor. That's 1 plus I to the power of negative n. Or, actually, an easier way to think about it is you can just divide the future value by that original accumulation factor. The critical thing to remember here is that the higher the discount rate you use, the lower the present value of those future cash flows will be. Getting that discount rate right is absolutely crucial when you're valuing any kind of future earnings.
Which brings us nicely to section 3, a centuries-old concept, the history of valuation.
Charging interest and compounding balances isn't some modern invention. It long predates computers or calculators. Way back in the Middle Ages, we were already seeing compound interest used in business deals. By the 16th century, scholars over at the University of Salamanca were fiercely debating how money's purchasing power changes and the whole moral status of credit. Then, in 1693, the famous Edmund Halley Yeah, the same guy the comet is named after. He proved how empirical mortality data and life tables could actually be applied to price annuities. Fast forward to 1930, and economist Irving Fisher publishes The Theory of Interest, which officially formalized this link between valuation over time, investment opportunities, and human impatience.
All right, into Section 4. Everyday time value, annuities, and real-world math.
We actually bump into these formulas constantly in our daily lives through things called annuities. Now, in finance, an annuity isn't just some boring retirement product. It's literally any series of equal payments or receipts that happen at evenly spaced intervals. So if you pay a mortgage, if you sign a car lease, pay monthly rent, get a fixed benefit pension, or even hold a bond that pays out regular coupons, you are actively interacting with the time value of money via an annuity. To figure out the present value of that whole stream of income, you have to individually discount every single one of those future payments back to today and then add the whole shebang together.
But here's the catch. Timing is absolutely everything. One tiny little detail makes a massive financial difference. Are you making those payments at the end of the period or at the beginning? If you pay at the end of each period, like you do with a standard loan payment, that's called an ordinary annuity. But if you pay at the beginning of each period, like paying your rent on the first of the month, that's known as an annuity due. And because that cash changes hands sooner, an annuity due is actually slightly more valuable. Mathematically, to figure it out, you just take the present value of the ordinary annuity and multiply it by 1 plus I to account for that extra little period of compounding. And finally, Section 5, the infinite math, perpetuities, and continuous compounding.
Let's push this math to the absolute limit and start with infinity. A perpetuity is a set amount of money that pays out on a routine basis and literally continues forever. Certain types of historical government bonds actually worked like this. Now you're probably wondering, how on earth do you calculate the present value of a payment that never ever stops? Well, what's truly amazing is that as time stretches out to infinity, that complex annuity formula we just talked about collapses into the simplest math imaginable. The present value of a perpetuity is just the payment amount divided by the interest rate. That's it. Payment divided by I. When time goes to infinity, the scary algebra just simplifies into basic division.
But what if, and bear with me here, what if interest compounds every single instant of every single day? Instead of chunky yearly or monthly payments, imagine your money growing like a smooth, continuous flow of water. To calculate this kind of continuous compounding, we have to swap out our standard numbers and introduce E. That's the mathematical constant used to calculate natural, uninterrupted growth. So the formula becomes present value equals future value multiplied by e to the power of negative RT. The R is your continuously compounded rate, and T is time. This specific formula is heavily used in advanced financial mathematics because continuous equivalents are just way more convenient to differentiate when you're doing calculus.
And that brings us to the ultimate evolution of this whole concept. When you get into advanced quantitative finance, the experts aren't just calculating a static flat number for present value anymore. They compute a continuous, shifting mathematical function. What does that mean in plain English? It means high finance treats the value of money like a fluid, dynamic mathematical wave that is constantly shifting over time rather than just a static pile of discrete coins sitting on a table.
So we have traveled all the way from a simple choice about 100 quid to literal continuous wave functions. But the underlying truth never changed once. Time literally is money. The value of your cash is constantly being pushed and pulled by the invisible hands of inflation and opportunity costs. So I want to leave you with this final provocative thought. Considering your own opportunity costs, how are you applying the time value of money to your financial choices today? Are your current investments working hard enough to outpace both your own impatience and inflation? Something to think about. Thank you so much for joining me for this explainer, and I will catch you next time.